Hello, everyone. Good morning, good afternoon, and good evening. Welcome to the AI and Machine 5G Challenge webinar series. My name is Thomas Baskol from the ITU, and it is my privilege to introduce today's webinar. The AI and Machine 5G Challenge is organized by the ITU, which is a United Nations agency for ICTs. The mandate of the ITU is to allocate frequencies to services that uses the radio spectrum, to develop standards, and to assist developing countries in setting up their ICT infrastructure. This challenge is kindly sponsored by Xilinx, and we are grateful for their sponsorship. The challenge aims at creating a community that will solve network-related problems using AI and machine learning. At this time, I would like to inform you that this webinar is organized in partnership with SG Innovate. SG Innovate is our Singapore colleagues who did their best to make sure that this webinar is, we have this webinar today. So I would like to invite my colleague Wei-Ming from SG Innovate to give a few remarks, as well as to introduce today's speaker, Singapore University of Technology and Design. So Wei-Ming, welcome and good afternoon.
Thank you, Thomas. So good afternoon, everyone from Singapore, as well as a big hello. Thank you for joining us for today's AI session co-organized with the ITU. My name is Wei-Min from SG Innovate. And a quick introduction about SG Innovate is that we are a government-backed deep tech investor and company builder whose mission is to help entrepreneurial scientists build deep tech startups that are looking to solve big global problems. Our work also involves building a global community of leaders, thinkers, and doers to drive and scale up deep tech innovations in areas such as AI, healthcare, quantum tech, and autonomous technology across various industries. So today, we are most glad to have Dr. Tony Quek, who is the Chair Professor, Director of Future Communications R&D Program, and Head of Information Systems Technology and Design, ISTD for short, at the Singapore University of Technology. I'm sure we have lots to hear and learn from him in this presentation. And with no further ado, do allow me to pass the time to Dr. Tony Quek. Dr. Quek, please.
Thank you, Wei-Ming. Let me share my slides. Okay, I think so good morning to all of you from Singapore. So today I'm going to share how AI, machine learning, or deep learning can be applied in communications and networking. So if you look at wireless communication systems, right? In fact, we have very accurate mathematical models. We have models that talk about capacity models, detection model, estimation model, networking models, and a lot of times models actually have been built very accurately in most scenarios, and that was the fundamentals that built our second generation, third generation, fourth generation, even 5G. And a lot of time, optimal solutions are known for various situations. That's why our systems are actually operating quite efficiently. And what's actually unique about wireless communication system, there's a lot of design constraints, right? Power constraints, there are delay constraints, latency constraints, and different constraints, right, to implement a practical hardware. So what is the use of really AI or machine learning or deep learning in such a systems? You can think about much more difficult challenges in the wireless context that cannot be solved with current system. For example, problems that is very difficult to model. There are problems or systems that is computational, infeasible, expensive to use optimal solution, or using AI or even deep learning or machine learning to efficiently optimize systems, or even dealing non-linear or coupled problems. So we'll look into the next few slides, some of these likely applications, and I will go into some of these detailed problems for the rest of the talk. So very quick overview, this is only slides that actually I'll give you an overview. I'll talk about different applications of this. If you think about AI, machine learning in the context of wireless system or communications, actually can implement centralizedly. So you have a very kind of server, or you have a controller or access point. So this is one structure, or you can do distributed, where multiple nodes or multiple server communicate or interact with each other to solve a problem, optimization problem, or you can actually have a structure is federated, where you have a server interact with different nodes where the model have a common model and data is located at each of these smaller user. And to actually implement these algorithms, you can actually do it offline or you can do online. Offline, you can do supervised learning where the data is structured, you have a no model, you can actually train your model to actually run in a very efficient way. Or you can actually, in a certain case where the source is actually structured, is very unstructured. So you have to run in an unsupervised manner. Or if you want to, for certain applications, because of latency constraints, you want to actually run online. So you actually can apply reinforcement where you have to define a reward function, feedback data, and interact such that eventually you will converge to a certain transfer function. Right? So this is some very one slide that have an overview of this AI or algorithms in communication networking. So what is potential use cases? So that it's not exhaustive. I'll give you some examples. Then I'll just elaborate a bit on that. For example, MIMO. It's very clear that wireless systems currently or in the future will use multiple antennas. You have more and more antennas. So feedback, compression, prediction will require a lot of overheads. So how do you actually can use machine learning or AI to help us to actually do it more efficiently? Channel estimation similarly, because the elements you need to estimate is a lot. Can we do it more efficiently? Because of the use of millimeter wave, where you actually has a lot of a beam that you need to manage. And when users are moving, so mobility management, beam management is one. And because of the number of users, finite interference, how do you manage interference and so on? Then your position location, resource location, dynamic spectrum access, network and RAN slicing. So let me give some examples and I just elaborate, right? As I mentioned, you can actually have a supervised learning approach, train neural network to predict, for example, WMMSE, weighted minimum square solution, or you can have an unsupervised learning approach to solve actually optimization problem, for example, in the wireless context, sum rate maximization problem. So these are works that has been done in the past few years, and there are more works in this context. There's one example. Receiver design end-to-end communication system, where can I replace my transmitter? Can I replace my receiver? Can I couple my channel estimation together, transmitter, receiver? You can actually have a supervised learning approach where because of you understand the channel you're in, there's a well-structured data, you can actually use supervised learning. So there are some examples of OFDM, different kind of channel models, and so on. Or joint transmitter receiver design. So you couple everything together as one. We'll show an example later in the context of visible light communication, where such a scheme actually outperform what current systems has. So the question is that what are the key challenges, right? So we see that there are many particular what I've shown is more of physical layer application of AI and ML in the physical layer context, but overall, what is the challenge of actually applying AI or machine learning in general? If you think of it, a lot of times the performance is dataset dependent, right? For training, whether it's structured or unstructured. So in order to actually allow this to be used in, for example, in 5G and beyond in a standard, so you have this standardization called 3GPP. So there's a 3GPP organization that standardized, for example, 5G, 3G, and 6G for. So essentially, I think the key challenge is that currently there's no common data set available for different use cases, whether it's autonomous vehicle, URLCC, massive IoT. So essentially there needs to have a common data set where everybody agree and is being used in the standard. Then your algo can be designed according to that data set because the performance actually is highly dependent on that. So that's one challenge that we need to overcome. The second problem is that this model generalization, right? Because a lot of times the environments that we are is it's keep on changing, right? Various wireless conditions. For example, if you want to design an end-to-end system for non-terrestrial applications, for example, that covers satellite, low-orbit satellite. So you imagine the wireless, because it's actually the wireless channel conditions depend on different heights, right? layers, and also depends on weather, whether it's cloudy day, rainy day. So essentially, how would my model generalize and fit for different conditions? So there's the concerns that offline training will not done well if certain situations changes, right? And another important factor is the lack of theory and some boundary analysis to understand, right? So a lot of times we need to do a lot of tests and sufficiently test to ensure that all cases has been covered. But how do we know we have done sufficient? What is this limits? So, and there's no evaluation verification methodology in the standard. So once you have no such a evaluation and verification model, there's issues like what about robustness? Is this secure? What happens if breakdown? So there's a sort of issues that we actually need to overcome. And if you look at the algorithms that actually applying now, a lot of times, particularly in the case of complex situation, you are using a data-driven approach, right? Using deep learning. So training, you require training. And training requires overhead. It requires latency, especially if I want to do it fast. How do we actually train with acceptable overhead and latency? That's also a challenge. And certain algorithms are highly complex, right? It's computationally expensive. It may be able to do it centralizedly. If I want to do it at a federated approach or distributed approach, is it feasible? So these are issues that actually also related to our network structure. And I mentioned this robustness, particularly related to this lack of theory. So these are the key challenges that in the community, whether it's academia, industry, or the standardization body, needs to overcome this for actually AI or machine learning to apply in the wireless communication systems more widely. But we believe that we will overcome this in the years to come. So many research topics, I will not go into detail everything. I'll just highlight some examples that we have done, particularly in a few, particularly related to our research. So one example is to apply this into a context of visible light communications, right? What is actually visible light? So information is conveyed through actually temporal intensity changes in optical pulse, LED, right? You switch the current LEDs on off at a very high rate. If essentially your eyes, your human eye will not be noticed, but essentially you're transmitting pulses, on-off pulses. What are the applications, right? Vehicles communicate with traffic lights, underwater, hospital, aircraft, and so on. So, or indoor scenario. So if you model such a problem, it's actually a very typical communications problem. You have message coming in, you do some encoding as a transmitter, then you have a sequence of the code word length, then you have an optical channel. We will describe the optical channel in details later, and decoding, and this is my decoded message. So I will have some dimming constraint because I will not switch on all the LED lights at the same time. So you can think of it as some power constraint. So I can define this as an inner product of vector of 1 and SP. So as I mentioned, what is my noise? What is my channel or noise model? So this is my transmitted set of symbols. This is my thermal noise. And for this VLC, I have another noise, which is a short noise. Actually, it's a non-linear noise that actually depends on the intensity of my input. So which makes this problem a highly non-linear type of problem, which DR or machine learning or deep learning would be good to apply to this. So what is my problem? It's a non-linear problem. I want to find an efficient encoding decoding strategy for this model to minimize a function, which is a symbol error rate. For this case, it's a nonlinear function under this dimming power constraint. So in this problem, actually, there is a code that is called constant weight code. The characteristic of this code is that they have the same Hamming weight, the number of ones. The mathematical properties has been intensively studied. We understand actually the fundamental limits of such a code. They do exist, but there's no optimal encoding method available. So can I use AI or machine or deep learning approach to do that? Yes, as I mentioned, I can actually use an autoencoder model. So this is a supervised approach where I replace my transmitter with a neural network. I replace my receiver with a neural network. But what is different? Because I want to capture the characteristics of my channel, which is my noise, thermal noise, and a short noise. So I have a structure. So what is actually unique about this is that because my sequence of my S are are all integers, 1 and 0, right? So if you understand this neural network, all these sequence are real numbers, but then I need to do a process, right? A binarization layer here. So the question is, can I do a very naive approach, right? I look at my numbers coming in the neural network, and then I want to quantize it, right? I can do some very simple, trivial unit step quantization, but then what happens? Because you understand that I'm doing an autoencoder. So it's actually I'm running through this stochastic gradient descent, and depends on the gradient. If I do that, then my gradient will vanish. And you know that if it ends at a very lousy point, then you will stuck there. So the performance will be very bad. So I can't do that. So can I actually do better than that? We actually can do it because it's a soft binarization approach. So if you look at this function, it's a sigmoidal activation function where you tune this delta. As delta increases from a small number 1 all the way to infinity, it approaches the unit step function. So it's something I can tune. So how do I use this? So essentially, instead of just running once, can I initialize it in an iterative method? So I run it one time, I train this autoencoder, I initialize another time until my performance is getting better. I'm closer and closer to the optimal point. Then I'll stop. Then I will use my output, which is follows my teaming constraint. So this is successive pre-training and fine-tuning. And you see that actually it performs much better than just do a simple hard binarization once. So how does this perform? Actually, we run this autoencoder. This is just a minimum harming distance. So we actually compare with what's actually known in the information theory results, and actually fits particularly well. Then we apply it to actual systems. So this is a different weight, different length, and this is the average simple error rate, and it performs actually well. So we see one example that actually can apply to cases of nonlinear problems. So this is just one example of a wireless problem that you can apply. Now, the second problem is this distributed learning. I'm going to apply distributed deep learning in an optimization problem context. So this is one optimizations problem. I just want to elaborate the notation. So E is expectation over this my random variable A. This is some function that depends on A and X. My optimization variable is can be a vector of X. And this is my another constraint is also depending on this A, which is a random variable under this constraint. So so can I solve this problem using neural network or deep learning? Why do I want to do that? Because if you look at this function, this is the expectation. So certain cases with this function, you have a very ugly function, which is a highly non-convex, or sometimes you can't actually get this expectation function. So can I actually replace this with a neural network to solve this problem? So this is basically the context here. So I'm going to find a generalized optimization framework, particularly for centralizedly and distributed, and particularly in distributed context, as I showed just now in the overview slides. You have this node exchanging information. What happens is this exchange information has to be quantized because of hardware constraint. You can send basically the whole real number. Yeah. So I'm going to use a neural network to solve this. So let's give an example. I'm going to give just a distributed wireless network example. So this node 1, 2, 3. A1 is my observation. So this is a random variable. At each node, I see some observation. You can have a vector form. For example, channel state information, the channel conditions that you see at each node. Then I have a local solution, optimization variable. I want to optimize at each node. All right, X1, X2, X3. For example, a resource location strategy. Then I need to exchange this information across the node because we have a solution, globally solution that actually maximize or minimize my objective function for this network structure. So I will have some constraint, right? These are my backhaul capacity constraint, right? If this capacity is infinite, then I can send exactly the whole number of A or X over to the other side, right? If not, I have to quantize it. And you can think of this backhaul constraint, right? For example, you are not using fiber, you're using wired backhaul. So I'm going to formulate this this wireless network into a problem. So if I do this problem in centralizedly, I can notationally write as what we see, we call it P1. The perfect global solution is my X. Of course, it depends on my A. It's likely a non-convex objective or constraint function unless your F is a very simple function, right? It's really not easy to tackle. Non-convex and unknown, especially, this is random variable, this is expectation. So this is my P1, P2. If I want to solve similarly problem, P1, but I want to have a distributed, right? Distributed where each node do some quantization, right? Of my quantization level L. This is my A, which is the information I collect H1, which is random variable. I quantize it V, then I exchange among them. Right, due to backhaul constraint, information exchange will need to be quantized. So this is my distributed optimization problem. So I'm going to use my deep learning approach. Because it's good at approximating unknown function. And the quality of approximation is addressed by this universal approximation theorem. Essentially, the whole idea is that if I can have more layers, you can think of it, more polynomials, right? More polynomials, then I can approximate some continuous function. And then I trained to produce an effective, a feasible solution. So what is the technical challenges in P1 and P2? Now, you see that my neural network now has to have long-term constraint, right? A lot of times works are on centralized, now I have a distributed, and also have binarization of DNN. So how do I solve that? So for the centralized solution, now we see that, because it's a difficult function, can I actually now convert my optimization variable map into a DNN parameter, right? So it's more tractable. So I run some new deep neural network for that. But now I have constraint, right? So this unsupervised approach, I have some constraint. So how do I tackle constraint in this? Now I'm going to tackle the constraint one by one. First of all, a projection activation layer, right? So this is basically an operator where I project onto my convex set at the outer layer, output layer, and this will actually capture my last constraint, which is my short-term constraint here. So I'm going to use this as a projection layer. And this is a convex projection, and it's realized by linear operation. So my gradient is well defined. I can run my stochastic gradient descent. So essentially, you can think of my one constraint is actually being mapped into my projection layer and my neural network, which means that my problem end up just have a minimize of this function subject to just one constraint. So how can we solve this? My conventional approach is I'm going to use a penalty training. I just bring this up to an objective function that have some parameter, and I want to do hyperparameter search, right? Just one approach, but may not be optimal, not guarantee it's feasible. So can I do better than? In fact, actually, you can do a Lagrangian duality approach. So that I'll not go into details, but essentially, in certain scenario, you have an optimal solution. For example, this is a classic non-convex spectrum optimization problem. But by using this method, in certain conditions, you actually have optimal solution. Likewise, for this case, when you apply for a non-convex, certain conditions, of course, you can have an optimal solution. And with that, I put everything together. I can run this something called primal and dual update method, and this is very efficient because now I run my DNN parameter together with my dual variables jointly in a single stochastic gradient rule. So there's primal update, there's dual update, and I can run this stochastic gradient descent. So this, if you're interested, you can look at the papers in more details. But I'll just give some examples. So this is some parameters we use. This is a typical wireless channel model, sum rate maximization. This is a highly non-convex problem, particular, especially I want to do an expectation H. H is my random variable. And you may just look at the H here. So it's a highly difficult problem to solve. So if you see that if I go to run this in my deep neural network, the WMMS, so this is the solution, best solution that being proposed. It's not optimal, but if I run my neural network, actually it's performed very well, much better than my local optimal solution. So this is just one example that actually, in some cases, actually perform much better. So this is an example of the distributed structure. Then I'll give another example of scheduling for federated learning. So as I mentioned, there's different ways of implementing machine learning. One context is this federating structure. What is this? Essentially, the whole motivation is that data, you don't want to share data. Data is actually allocated at each user, for example, each handphone here. So each handphone will run the neural network, assuming that everybody has a common model, but data is just located at yourself. So you run it. So then you have these parameters, right? Your neural network parameters. So you're going to upload the parameters up to a access point on the controller. And with all this aggregated weight, I can do a weighted average. Then I'm going to iterate this process. In cases where this link from all the users to this controller is, let's say it's perfect, it can be wired. Then after sufficient iteration, actually I can converge to a global solution as if everybody is co-located at one place. So I can solve different type of problems, different models you give me. But in a wireless context, what is different is essentially the communication from all these users to a central will go through a wireless link. And you know that medium, communication medium is shared, is resource constrained, is subjected to interference, and you will not choose all the devices at the same time because the spectrum is limited. Right? So each update you need to schedule. So the question is how to schedule them, how do you actually choose them, and what's the effect of interference? So can we model this? So essentially you can think about in the context of this mobile edge network. So I can model my access point, the controller as a person point process, then each person point process is randomly deployed in a network. And each AP has a K-associated user, which I show here, right? Each one run a model, then it will send up the weight. Then in each network, the spectrum is divided into n channels, where n is actually smaller than k, where k is large, right? So, and I assume that all this spectrum is reused at all the different cell location. So I have an interference problem because it's actually globally reused. So the question is, how do I do scheduling, right? The AP can do uniformly schedule. I select n out of k, or I can do a round robin. I divided all the users into a group, then I sequentially select, or do proportional pair scheduling. So I choose n out of k. What is my criteria? Example, the strongest signal to noise ratio, I'll just choose them. So it's an example of tree scheduling mechanism. And what is actually different from the conventional federated learning is what is the criteria that train update is successful, right? The train update is successful if and only in a few conditions, right? User is being chosen. I've been chosen to send to my access point. And when I send to the access point, because I'm sending over to through a wireless link a packet, so the received signal to interference ratio needs to be above a certain threshold in order to be successfully decoded. So these criteria need to met, and my metric is to quantify the number of rounds I need to do in order to have a epsilon accurate solution. Right. So I'll not go into theories of this that you actually can derive them, but that's what is interesting. It really depends on how good the link is, right? If I'm in a very high SNR, SINR or SNR scenario, essentially what is the best scheduling? It's proportional pair scheduling, right? If your channel is good, I'm going to do. So it gives us insight. So if I have millimeter wave, right? I have millimeter wave, then essentially I can ensure that my beam is very sharp and have a very high SNR, then I can do this proportional pair scheduling mechanism for federated learning for training. Well, in a certain case, if I don't have that technology, then I'm sharing my spectrum across all the users and it could be interference limited. I'm low SNR, then I want to do a simple round robin scheduling. So I don't need to do some sophisticated scheduling, and that's more efficient. So this gives us some insight of how to actually implement in the wireless context. This is the last one I'm going to just share. Is this random access and the application for in the context of wireless. So this conventional random access. So imagine a lot of IoT, current IoT, I have a cellular base station. I want to actually send a packet. So can you just send immediately? No. So you have a process called preamble. So you need to select some preamble. Then I'm going to use this preamble. I'm going to tell for example, a base station, I'm going to send this packet. So what is the mechanism, current mechanism? It's actually a very simple mechanism. It's this active and non-active, right? So there's only two ways to separate, whether there's people sending or people not sending. If it's active sending, then I will capture, oh, okay, where you are, then I'm going to schedule you. Why is it that? Because the current mechanism is a very simple mechanism. It's called a threshold-based preamble classification, right? For example, a node X, for example, here, it utilizes a preamble, right? You can imagine it's ID. I choose a preamble 2. Then I'm going to send out. So at the base station, then essentially you will classify active or not. So you do some thresholding, do some threshold, and oh, you're above my threshold value. I detect you, so I know, oh, there's someone sent. Okay, but what is the problem with this is that what happens, because it's a many sense, many IoT devices, they are, just imagine Y and Z are actually not co-located together and they don't talk to each other. And randomly they choose the same ID, for example, preamble 9. They'll just send up to this base station. Oh, but then at the base station level, I will see this threshold as active, right? It's still above. So I will not know whether it's one guy sent, or two guys sent, or three guys sent. So that's a problem. What happens with that? So in the case of one user, it's fine, because one single user, then the base station, oh, then you'll tell this guy, oh, you can just transmit your packet. Then this is a data transmission link. Oh, so it's okay. But in the case where you have two guys who collide, the base station will not know. So your broadcast tell them, oh, please choose preamble 9, this ID 9. These two guys who doesn't know that actually they collide will just choose the preamble 9, then they will just send the packet and you'll collide. Once the packet collide, you have interference and essentially cannot decode. So you waste your time, right? So this is a conventional approach, which has a problem as you have more and more device, massive device. So can we do better than that? So you think of it. So what is this having two packets choosing a preamble? So it's imagine this has this waveform, right? Continuous waveform. If we are able to have sufficient training data and we know that, oh, the waveform of these two guys who collide looks like that, then three guys look like that, four guys, can I classify them? Yes, because in fact, these are continuous functions. You have sufficient trained data. Then it's essentially the whole idea is this deep random access. It's a classification problem where I can do a preamble classified whether there is one guy sending, two guys sending, or three guys. I can actually do more than that, because if you think about it, there is this waveform presence of the distance, right? So this is called timing advance, how close you are. But because I have sufficient data, I also can actually look at, predict, oh, you're so far away from me. How far away from you? So actually there is also this timing advancement classification. So we can actually do this classification. The key thing is, once I have sufficient data, then I can do scheduling. So if I prepare this, then how do my model will change? My model will change compared to a conventional. Actually, I can a simple one, I have one non-active, nobody's transmitting. Collision free, one guy transmitting, and I know actually exactly where you are, then I can do scheduling. If two guys transmit, in fact, because I look at the waveform, I'll classify at the base station, oh, I recognize actually you're colliding. So I will not tell both of you to schedule. So then it becomes more efficient, right? So this is a multi-class classification model I have. And this is an example, right? So if there's one guy, then I know, oh, you're just one guy. If two guys choose a preamble because of my structure, my intelligence and neural network, you're able to classify, I know you two choose a preamble. Then I will not waste my time to tell you to actually transmit. Or in fact, I can also make this more sophisticated in a sense that, oh, I know you two are transmitting. Then we have extension of this. Then I know, oh, it's okay. Then I can adjust your power so you can still transmit. So there's different way that I can add intelligence on that. But this is the first most basic scheme. So you run some simulation setup. So there's some training set, some test set. I just use a simple K model. So then we have channel models. As I mentioned, you need to have some common channel models that is being used. Some number of nodes. So huge number of nodes, because I'm interested in the case of massive devices, this is arrival rates per minute, number of attempts, and so on. So we see that a conventional border, as I increase the number of nodes, my delay will increase. Then if I use my detection scheme, where it's the case where I detect there's collision, then I will not schedule. So this is a red case. The black case is I have a resolution. If I know your collision, then I say, okay, it's okay. Then I will schedule two of them orthogonal in a way. Then I actually can resolve this. So by having some intelligence classification coupled with your random access protocol at the base station, then you actually can resolve a massive IoT scenario. So I'm a bit quick, but I can have more time for discussions and questions. So what is how do I actually use this AI or machine learning effectively, particularly in the context where it's 5G, future communications, and network? As I mentioned, we really need to understand where to apply. Although we have shown you certain cases where we can apply or you can perform similarly or perform better, but we really need to understand when to apply, because there's a trade-off, there's complexity issue, how to apply. Because by applying this, for example, I need data. As I mentioned, I need to have training data. I need to have computation to run it. What is the cost of applying? For example, in the case of distributed, I need to exchange information among them. So there's a cost. The complexity of applying that, for example, in the federated learning context, the complexity, I need sufficient iteration among the user to the access point. So there's a complexity, time involved. The robustness of that. What happens in a certain context, we see that the users are fixed. What happens? Users come and leave the network. How would it affect your algorithms? Is it still stable? What happens if some algorithms have bad data injected into your algorithm? So there's issues of all this robustness, security. So there's many interesting questions still remain. As we see, I think what I want to basically end, and I can open up more questions, is that while we look at these tools, it's also time to relook at how we do things, our conventional wisdom in doing things. Maybe it's no longer optimal. So it may allow us to do something very differently. Particularly, as I mentioned, maybe I can go to this slide and I can open up for questions, which is this slide, which I think likely the value of this is to actually apply into all these 4 cases. Cases that we can't model, because problems that we can model, we can use a conventional method. Cases where optimal solution is too expensive to run, especially for the non-convex case. Can I do this in a more efficient manner? Can I optimize this, particularly as a tool to help us? Or cases that are non-linear, for example, the VLC case. It's a non-linear problem. Of course, it's not coupled here. If you want to couple, then you have a multi-user case. It's a coupled problem. Can I use this to solve better than that? And I'm open the floor for any questions. Thank you.
Thank you so much, Prof, for the nice presentation. I would like to go directly into the Q&A, so I'd like to invite my colleague Vishnu. Vishnu, good afternoon and welcome. Take over for the Q&A.
Yeah. Thanks, Thomas, and good afternoon, Tony. Thank you for coming. This was a very interesting presentation, in which you talked about very relevant use cases. Actually, we should have. I am now thinking that we should have had this conversation long back, because we were actually wondering what kind of use cases exist, and you have correctly called out some of the very interesting use cases for us. I want to ask you about federated learning first. You described the mechanism, you described some of the use cases, but can you combine it with the cost of applying? Because one of the points that you mentioned is also about cost of applying this. So one of the things which standards bodies like us is looking at is the type of interaction which is required between models,
Yes.
and what type of parameters is required to be exchanged, and what is the cost in the sense of network cost of transmitting it and receiving it. Have you come across models which capture this kind of information? And if you combine it with your studies, so that is in terms of the other use cases that you mentioned, right? Very interesting studies. So they are, for example, random access, right? So if you combine these two, you get a picture where there are models which are running in a distributed manner, and you have these parameters which are exchanged potentially over there. So that's where the problems comes. So what is your opinion about and how to model, first of all, how to model this problem? And secondly, are there optimizations possible there, and what kind of optimizations would you suggest to be applied in this problem space?
Okay, so maybe I can answer this in a few approach. One from let's say from an industry or standardization body approach. I think the first question the board, all this organization body needs to agree upon is that whatever all the different companies agree on, the protocol or the amount of information exchanged among different modules should be independent of the algorithms and the model, right? So it should be agnostic in a sense, because then you will actually be able to generalize, because we will not know what are the applications available. And also what they also need to agree upon is this exchange of information will be needed to actually generalize into, for example, currently how fast things to be exchanged, maybe at a low rate, at a medium rate, at a high rate. Why? Because I will see that certain applications will require very efficient exchange, right? Their model may not need to converge, because some applications will need non-optimal solution. They have a rough idea, they would be running, because you probably will not be able to wait until the optimal solution. So I think from a standardization body, I think what will be need to agree, whether it's federated learning concept, distributed, centralized concept, is what needs to be exchanged, the kind of information needs to exchange, how fast is it to exchange, and the feedback, because you need to have the feedback. A lot of times, if you run centralizedly or you do experiment, you always have the feedback. It's actually a Gini feedback, we know, right? Do it offline. But then in the actual scenario, let's say autonomous vehicle running on the road, that feedback is important. If that feedback is breakdowns, or that feedback is not regular, we do not know how to fine-tune our algorithm. So that's important. From academia point of view, I think yes, I think it's right. It's actually, the question is that as I mentioned, we really need to understand when and where to apply and the constraints we have, right? So the example that I studied Federated is very simple model. I have not taken into account, for example, latency constraint, the power constraint. And if you think of it, if I have interference issue, I have latency issue, and then I think the whole algo will be design will be different. So that will actually have lie down to the application. So it goes back to my question that I have to mention. If all this needs to be standardized in the future, then the community for all the use case, for example, release 17, there are all these different use case, whether it's autonomous vehicle, drone, factory, they should start having a common data set, where this data set is agreed among everybody, and this data set can be used by everyone to develop the algo. Once you have a common data set, then the next thing is with this algo, then with your different wireless weather scenario, see how it performs well. So I think yeah, so that's why I want to I hope I answered the question, because quite long a question.
Yeah, I think you captured it quite well, especially the part about approximation, right? I think that's holding the key here. I would like to, perhaps we can talk offline and follow up about what kind of research is happening in that area. It's quite interesting area for us, and we would like to see optimizations in that space. There is a question about how to extract data, how will data extraction be achieved, and what is the mechanism for data extraction. I think you did talk about online and offline mechanisms, right?
Yes.
I would want to add to this question that dimension also, and I would like to hear your views on what kind of techniques we can use in case of online and offline training, and as well as in terms of data models, because extraction is one part, but also I think you mentioned it in one of your early slides which you showed. There was one point about data models. What is your opinion about these points? One about data extraction, the mechanisms for data extraction, and standardization and availability of data models.
Okay, I think the most difficult challenge is the availability of data model, because data is sensitive, right? A lot of times data is precious to a certain different industry or different use case. So I think this is the main challenge. So I think the community needs to agree on creating this data set, whether it has to be created by industry or created by some university or government agency. I think that's the first thing, to have that data set, and then the data set has to be related to certain applications. Because if you think about, we have to really look at how the machine learning or this deep learning community becomes a big hype. It's because of the data that certain researcher in US created a huge amount of data set that drives this whole areas of vision related. Because with that data set, essentially people see that actually it becomes so powerful that a lot of classifications, a lot of vision related applications become so accurate. So I think that is the key, that the community, unfortunately that data set was created from a university, whether university will want to do that, and that has to be related to an application, right? For that context is vision. So in the context of us is that, let's say if it's related to channel measurement, right? It's related to the MIMO context or related to millimeter beam alignment, then we have the 3GPP or this community needs to is essentially agree on the common data set among that. So this has to be done at the standardization body in order for this to work, right? So I think that's the data part. So let me see. The question is, yeah, so the data has to be contribute actually for all the different stakeholders that involved, right? I think there are some, because we see clearly, particular in this May, June, we have this release 18 first workshop. Interesting, we see a lot of contribution from different companies. Particularly if you look at round one, which is related to physical layer, you see that they actually, a lot of companies are actually interested to apply AI into this. So hopefully in order for that to be actually becomes a standard specification, all these companies that propose would actually have to contribute to the common data set. So in order for this actually to be in a standard. So I think at least we're happy that there's some movement along this direction, and all the companies are agree upon that. Yeah.
Thank you very much. Yes, I think Another question was about big data, and I think that classifies as what you called as capturing the data in data lake and applying it, analyzing it and applying it in various parts of the network. But I would also, in that case, I would worry about the granularity, accuracy, and the quality. Yeah, exactly. So the quality of data as well as time synchronizations, because most of these data lakes hold data perhaps which may be no more relevant. So what is your opinion, and are there, first of all, simulation techniques which we can apply to quantify any of these? Could you talk about some of these aspects?
I think it's a good question, because that is the difficult part. Because it boils up to, in the end, whether in a sense that if you use this at the network level, it's fine. For example, at the slicing level, where the time scale is not so long. I mean, the time scale is not so short. So in a sense that or certain application layer, yes, I think that would be fine. But if you want to go all the way down to the physical layer, where and certain application where in fact you need to have very tight latency constraint, the challenge is, can you do that? Because you need to have you need to really dynamic adapt to that. So it also boils down to my last slide summary, in a sense that we need to understand, maybe it's not the best to actually apply to all these machine learning AI. In certain scenario, we may not want to do that, right? Because if not, we will have a very sophisticated end-to-end system, very connected all the way down to the especially your granularity, as you mentioned, right? It actually has to be very and the data will be changing, right? So depending on the dynamics. So I think so I think instead of that, I think it will go back to very basic. It's the use case, right? Certain use case where people see that likely we're going to use that. Then the use case is created a data set. So I think people are looking at certain use case, definitely we would like to use because the current approach is conventional approach is too complicated. For example, the massive antenna channel estimation, I think that one is relevant. At the slicing level, can I use some of this approach, machine learning approach or AI approach, to help me to actually do my resource allocation more efficiently? Correct. So I don't think I need to use AI or machine learning everywhere. So I think the point is that because we really need to think about complexity and the robustness issue. Yeah.
Very good answer. Very good. I think that's a practical way of looking at things. I think latency is a constraint in certain, yes, especially in physical layer, especially at the edge. I think certainly this is an important criteria for us. Another part is the resources required for training itself. This is again coming back to what you explained earlier. So training requires certain resources which may not be available, and data may not be, we may not be able to send it out. So it's a kind of a catch-22 situation there. But I think, as you explained, maybe the choice of use cases will drive this data availability and the AI ML techniques. I want to ask you maybe one last question, which is about one of your early slides. So I think in one of the slides you did mention about the various use cases, and you did talk about I think use of AI in various blocks. And one of the techniques which is happening now is AI based design, especially in physical layer, We have seen
Yeah.
papers coming out about AI-based design of physical layer, as well as, other use cases that you explained.
Yes.
So what is your opinion? Is there a contradiction there in terms of designing these layers using AI, and how can is that a recent or a short-term thing to do, or do you think that's more in the future? And where do you see that research going? Actually, one of the things is very ambitious of replacing different blocks even in physical layer with AI models, right? there are many papers on that subject itself. What is your opinion, and what is your thought on such application of AI in designing the blocks?
Okay, I think a lot of times when we look at technologies, right, or different all this new invention, innovation, I think it's not good to have a cool technology or a cool innovation. I think it has to be stem out that is a problem. That means there is a fundamental problem, then we have a solution or technology that solve it. So likewise, so although there are many papers out there, of course there are some papers actually they are solution, but they are looking for problems, or in fact there's no problem. Conventional approach has. So as I mentioned in the first slide, so a lot of our wireless communication systems, they are models that are actually well defined, because we have so long theory, so much theory and so much known result. So there are certain cases where you don't actually need to have AI. For example, point to point, I have two antenna or just single antenna. You will not want to replace with a AI or deep learning, because that you don't have a problem there. So I think, but then what happens if conventionally we always assume a linear model, for example, whether because particularly because non-linearity is very hard to model, right? And then for these cases, our solution becomes not so optimal and not so efficient. Then with machine learning or AI, because of sufficient data, can it be used to tackle all this non-linearity or coupled problems where we can't model? So I think we should target particularly on such problems. Then if the solution perform much better than conventional, I think this sort of physical layer approach will make sense. So this is one example. So we can't just look at all the conventional method and replace. We need to look at what is the value of replacing. If there's no problem then what should we replace?
Yeah. Thank you. I think that's that will, I hope that opens some studies in this field. We look forward to those comparisons and use cases, as you say. I personally like the scheduling use case that you mentioned. I think it's a very interesting use case, and it also has many constraints which are quite interesting as well for us. So I don't see any other questions. We are almost time, so we want to, yes, Thomas is back. So I want to hand over to Thomas, and thank you for answering all the questions so patiently.
Thank you.
Thank you so much, Vishnu. At this point in time, I would like to give a very big appreciation to our speaker, Prof. Tony Quick, for the wonderful talk. I think it was quite interesting talk. The perspectives of AI in networking and communication, quite nice. Thank you so much for making time to talk to us.
Thank you. Thank you.
Yeah. I would also like to give a big thank you to everyone for attending today's episode in the webinar series brought to you by the ITU AI and Machine Learning 5G Challenge. And this special webinar was organized in partnership with SG Innovate. From me and my colleagues at the ITU AI and Machine Learning 5G Challenge, we would like to wish you a very good day. Bye-bye.